Passive video understanding is insufficient for evaluating real-time interactive AI assistants. Traditional benchmarks test models by asking static questions about a completed video. However, a true AI assistant must actively guide a user step by step. In real-world scenarios, the assistant's advice directly influences what the user does next. This creates a dynamic loop where the video content itself changes based on the model's previous responses. To evaluate this, we need a benchmark that simulates active, multi-turn human assistant interaction. The core challenge in evaluating interactive AI is the diverging path problem. When a user has a goal, like making a cup of coffee, there are many valid ways to achieve it. If an assistant suggests preparing the milk first, the user's next action changes. If it suggests preparing the espresso first, a different action occurs. Because offline datasets cannot dynamically generate new video clips for every possible choice, standard evaluation pipelines break down when models give unpredictable responses. OmniAssistBench solves the diverging path problem by using prior knowledge to enforce a single evaluation route. The researchers reverse-engineered existing internet videos by first defining a strict procedural path based on the video content. For example, if the video shows espresso being made before milk, the model is given this prior knowledge and must guide the user along this exact sequence. This ensures there is only one ground truth path, allowing researchers to use static videos to simulate continuous, multi-turn interactions. The benchmark features a two-tier framework separating basic perception from advanced goal-oriented tasks. The basic tier evaluates foundational skills like social perception, temporal ordering, and following non-audio prompts like hand gestures. The advanced tier evaluates higher-level capabilities. These include context-aware response, where advice must be tailored to the user's specific environment, proactive response, where the model must decide when to speak, and process tracking across long-horizon tasks. To mimic the complexity of real-world assistance, the benchmark includes 3 high-fidelity, long-form case studies. These cases are meeting simulation, blind assistance, and handicraft process tracking. In the blind assistance case, a user simulates visual impairment and asks the model to ground objects, navigate using a hand-drawn map, and proactively alert them when a specific person arrives. These scenarios require models to combine multiple perception and reasoning skills over dozens of interaction turns. Evaluation results reveal a massive performance gap between current models and reliable human-level assistants. Even the state-of-the-art proprietary model, Gemini-3-Pro, scored only 66.4 out of 100. The leading open-source model, Qwen3-Omni, Instruct, achieved a score of 51.2. While these models generally understand verbal instructions, they frequently provide incomplete or incorrect answers when faced with complex, multi-turn visual environments. Current Omni-LLMs face critical bottlenecks in context memory, gesture recognition, and proactive timing. First, models struggle with visual prompts like hand gestures, which are highly abstract and easily confused with background noise. Second, limited context windows cause models to quickly lose track of the initial user goal during long interactions. Finally, models lack inhibitory control. They struggle to delay their response until a target event occurs, often replying prematurely to irrelevant background speech. OmniAssistBench establishes a rigorous foundation for the future development of real-time interactive AI. By exposing the limitations of current models in long-term memory, gesture understanding, and proactive timing, this benchmark provides a clear roadmap for researchers. To build truly reliable assistants, future models must move beyond passive video captioning and develop robust, context-aware reasoning that can adapt to the flow of human life.